Okay, so if V1 equals 2, 3, and V2 equals negative 1, 4, then V1 plus V2, we would expect it to equal 1, 7, right? Because these are column matrices. We just add them as we would add matrices. We add them element by element, okay? And of course, we interpret vectors as arrows and addition of vectors as head to tail. That's exactly the way it works out, right? Because these can be represented in 2 dimensions by arrows, okay? And the arrows have these properties, okay? So 2V1 is 2 times 2, 3, which is 4, 6. This arrow is going to be the same direction as this arrow, but twice as long. 3V1 minus 5V2 . Okay? I think I did the arithmetic right. If not, you can correct me because you know what's going on. So it's obvious we can do all these things. Okay, so if you have 2-dimensional column vectors with the rules for addition and multiplication by scalar, right? Do these properties follow? First of all, most importantly, if you add 2 of them, do you get another one? If you add two-dimensional column vectors, do you get a 2-dimensional column vector? Okay? Well, that means that the set of column vectors is closed under addition. It's closed. You've got a club here. You add any 2 members of the club, you still get a member of the club. Okay? So, I'm going to write a little terminology here.
I guess I messed up some math on that last one. I got 14, negative 11. Or no.
Let's see. You got what?
On the last one, I got 14, negative 11.
14, negative 11.
As opposed to 9, negative 14.
Well, let's see. Negative 5 times negative 1 is 5, right? Negative 5 times 4 is negative 20. If we believe this, then that's 3 times 2, 3. I misread it. You can fix that. Okay? Yeah, I caught that out of my peripheral vision, and that's what I believe. Okay, so you can fix that. Now, more importantly than the arithmetic, because we know we can do the arithmetic, at least you can, let V be the set of let V be the set of 2-dimensional column vectors with the usual addition and multiplication, and I'm being a little unspecific there. You have to have a set of vectors and a set of scalars. The vectors are the 2-dimensional column vectors. The scalars are the numbers you can multiply by those vectors. Okay? Then this says Yes, sub V is closed. Under addition. Answer to this, you see, is just a number. You can multiply it by W1, just multiply both components by whatever C is. So these closed under multiplication by numbers. That was this question. Okay? So what property do you think this is? What are we doing here to say that this is equal to this? What's the name of the law that?
Distributive law.
Distributive law. Now we want to be specific. So multiplication by numbers distributes over addition of vectors. Okay? Now there are other properties, but these are kind of, in a sense, the main ones for what we call vector spaces. Okay? And all vector spaces act like vector spaces for numbers over column vectors. All vector spaces have these properties. Okay? If W1 and W2 are in your vector space, then W1 plus W2 has to be in your vector space. And multiplication by a scalar, in this case think number, but there are other kinds of scalars. Multiplication by a scalar doesn't take it out of the vector space. So the vector space is nice and compact, confined. Okay, it's closed. Okay, nobody uses the word compact, but that's topological implications that we don't want to confuse. Okay, and the scalars distribute over, scalar multiplication distributes over vector addition. Okay, so just taking these three properties, if you understand these three, and you can prove things about these three, you can understand the rest. So I'm going to say that, yeah, okay. I'm going to say that it's a bad color to use right there. So, probably not a good one either, but vector spaces. Set of vectors and a rule for adding them. Okay? set of scalars and a rule for multiplying vectors by scalars. Okay? It's closed under scalar multiplication. And vector addition. Scalar multiplication distributes over vector addition. Okay? Also, didn't give an example of this, but there is a zero vector. And every vector has an inverse under vector addition. So we're going to slap those on, and we're going to look at a couple examples of vector spaces that don't look like column vectors, but could be represented by column vectors in a way that's indistinguishable from what we do with geometric column vectors. Okay? So first example I'm going to use is polynomials of degree less than or equal to 2 and the scale is to be real numbers. Okay? And let's say, I moved to do complex value, but let's do real value polynomials of degree less than or equal to 2, so we don't have to worry about the details of complex numbers. Okay? Real value polynomials of degree less than or equal to 2. The scalars are real numbers. Okay? So what's the first criterion? Closure under addition of vectors. Okay? Well, can you give me an example of a polynomial of degree less than or equal to 2? Because we want to start with examples to get a handle on how we would prove this in general. Give me a polynomial.
X squared minus 3x.
X squared minus 3x?
X plus 2.
Plus 2. Well, okay. X squared minus 3x would have been fine, but that plus 2 makes it even more appealing. Okay? Okay. That's one. Now we have to do closure under addition, so we're going to need at least two polynomials, right? Or give me a polynomial.
I feel like whatever I say is gonna make this
Again?
problem really hard.
What?
I feel like whatever I say is gonna make this turn into a lot.
No, it's
more.
really easy.
Okay. 3x squared minus 2x plus 0.
Okay. So that would just be
3x squared minus 2x.
3x squared minus 2x. Right? Okay. Perfectly good example. We don't have to write the plus 0, it's understood. Okay? Well, can you add those polynomials? Okay, so let's let B1 equal this and B2 equal this. Okay? Well, what's it going to equal? What's V1 plus V2?
4x squared minus 5x plus 2.
Yeah. Okay. Well, that is a polynomial of degree 2. So, we're off to a rising start. So far, so good. First polynomial, first two polynomials we thought of add up to another polynomial in the set. Two polynomials of degree less or equal to, done, certainly added up to a polynomial of degree less or equal to 2. Okay, can you think of any polynomial of degree, any two polynomials of degree less or equal to 2 that wouldn't add up to a polynomial of degree less or equal to 2?
X plus 2.
X plus
2.
X plus 2? And what?
Well,
Got to have two of them.
that's a fair point.
Well, first place, X
2x
plus 2 is
squared.
of degree less or equal to 2, right?
Like 2x squared other stuff and negative 2x squared other stuff. Oh wait, that's
Okay,
still
well,
less
that
than.
adds up to
It's
0,
still less
right?
than.
You'd have them add up to 0. It's a good thing because you need a 0 vector. That's still a polynomial of degree less or equal to 2. Its coefficients are all 0. That's a perfectly good polynomial. And X plus 1 is a perfectly good polynomial of degree less or equal to 2. Its degree is 1. 0 is a polynomial actually of degree 0. Okay, that's less than 2. Okay? So we need to clarify that about polynomials and definitions. But now you should understand, and it should be pretty obvious to you, that no matter what polynomial's degree less or equal to 2 you have, you're going to get a polynomial of degree less or equal to 2. I mean, not so if you multiply them, but we don't multiply vectors. There's no vector multiplication. In some vector spaces, actually, there could be, maybe. Might not violate the rules, but it's not important for whether you have a vector space or not. Okay? I mean, you got dot products and cross products. Cross products are unique to 3 dimensions. Dot products are good in any dimensions. There's kind of a multiplication, and that's real important, especially dot products, which are really simple and have great implications. Like you can find the angle between two polynomials. So, I might not have time today to tell you about that. Okay? Okay, so right now we're just really trying to start to approach the whole idea of proof in the context of proving that some space is a vector space, or maybe that it isn't. Okay? And when you get your books, that's one of the first things you're going to get to do. Okay, well, if you think about it a little bit, you find that it's pretty obvious that if you add two such polynomials, you're going to get such a polynomial. But can you prove it? Okay, that just says it's pretty obvious the sum of polynomials of degree less than or equal to 2 is a polynomial of degree less than or equal to 2. There are a lot of things in mathematics that really seem to be true. It seems obvious that they are, and they aren't. So we've got to prove them. We've got to put it on a firm foundation of proof. And we actually prove this. Well, I'm going to prove this one for you. Then I'll ask you to prove the next one. Okay? Well, okay. So I'm going to say proof. First of all, an irrefutable statement because it's a definition. Okay? A polynomial of given degree, an application of that definition, has the form. And we could say, yeah, we'll call that a vector, just remind ourselves we're considering these things to be vectors. And we're proving that they have the same property as column vectors of numbers. Okay? Columns of numbers. Okay? So, let V1 equal A1x squared plus B1x plus C1. V2 A2x squared plus B2x plus C2. Then V1 plus V2 is A1 plus A2x squared, okay? And A1 plus A2 is still a number. B1 plus B2 is still a number. C1 plus C2 is still a number. So this equals AX squared plus BX plus C, where A equals A1 plus A2, B equals B1 plus C2. Okay? All real numbers and we're done. Because since these are all real numbers, I erased that comma because it kind of looked like a subscript 1, which might be confusing. Since they're all real numbers, this is a polynomial of degree less than or equal to 2. Okay? Make sense? How we did that? Okay. Now, I'm going to throw you to the wolves and ask you if you could prove closure. Closure under scalar multiplication. That corresponds to this one, right? A number times the vector has to be one of the vectors, right? So how would you write out a proof of that statement? Of that condition? So let you ponder for a minute.
I feel like this is one of those moments when I shouldn't have been
Okay.
writing.
Well, let me write a couple of things. I had a good piece of white chalk here somewhere. Not a box full of it, so I guess I can handle this. Feels like a full box. I have 2 missing. Now, capital V stands for vector space. And just to be sure we know when we're doing a capital V, I'll kind of write it this way. Capital V with an attitude. Okay? So what I would recommend you do is do an example. And then a proof. And I'll give you a little time to ponder what that might mean. And you can look at the other proof to see kind of the things we can do and the style of it.